In this video, we present the experimental results of our paper, Range Estimation and Impedance-based Control applied to a flying pirate robot interacting with the environment. The flying pirate robot FPR is a design where multiple quarters support collectively a moving platform with passive kinematic chains. In this paper, we apply an impedance-based controller with external range estimation to the FPR for performing disturbance rejection and robot environment interaction. In the first experiment, we flew the FPR to perform a hovering flight with an additional payload considered as a disturbance to the robot. A first test on the initially proposed PD controller was implemented. We show here that the pre-tuned PD controller can well perform the trajectory tracking task in free space without any disturbance. However, an additional payload of 300 grams corresponding to about 3 Newton external force can easily degenerate the tracking performance of such controller. At the same time, the performance of the PD controller with feed-forward external range compensation is not much enhanced, especially for tracking of the desired leg angles as shown in this video. In contrast, the impedance controller can better control the robot state in presence of external disturbance, showing its capacity of handling interactions with the environment. During the second experiment, we tried to analyze the behavior of the impedance-controlled FPR with varied impedance gains in presence of external wind perturbations at about 26 km per hour. We remarked that a good compliance behavior of the robot is ensured with lower stiffness, especially shown by the response of the platform orientation state. On the other hand, higher gains in stiffness coefficient will allow the FPR to have more resilience against the perturbations. As for mass coefficient, higher values might be beneficial to the robot to reject the disturbance. However, the robot becomes less reactive to the external effects as well, which is undesired for the interaction tasks. We found in the experiments that a proper value of the mass coefficient corresponding to the system's inherent properties is more preferable, rather than tuning it for rejecting disturbance purpose. In the third experiment, we show several contact-based interaction tasks performed by the FPR. A cylinder foam antifighter is mounted on the platform to achieve the contact with the board hanging in the air using tightly stretched ropes. 3 interaction tasks were performed with different robot configurations and interaction scenarios. In the first task, the platform is controlled to contact with the board in 2 different orientations, one in flat orientation and the other inclined of about 10 degrees in roll and 25 degrees in pitch. The desired contact force is sent by an operator, with the impedance controller stabilizing the robot configuration and regulating the force tracking. The results of the force tracking and evolution of the platform position are shown in these figures. The shaded areas in orange demonstrate perform steady interactions with the board. This task shows the FPR capable of pushing a certain amount of force up to 10 Newton in different orientations. Then we test the FPR to perform pushing and twisting tasks. The operator controls the desired contact force the platform is expected to exert on the board, while sending the yaw and yaw rate commands to twist the platform during the steady interactions. The figures demonstrate that the desired contact force and the desired yaw movement of the platform have been well tracked during this task. We can see from the video that the robot states such as leg angles and the platform orientation is stably controlled during the whole interaction task, with contact force exerted on the board up to 6 Newton. The third task involves a more challenging scenario where the FPR is controlled to perform interactions in presence of external perturbations by winds at about 13 km per hour. We showed that the robot can well perform the contacts with properly defined impedance gains, with tracking errors of the desired contact force and the platform position remaining in acceptable range. We remark, however, that several interactions were interrupted by the operator for safety reasons, as the tracking of the interaction position along x-axis were perturbed by the winds and the contact point was close to the edge of the board. But the robot's behavior still remained very stable during the time when the contacts were performed. All the tasks were successfully accomplished in the experiments, validating the effectiveness of the impedance controller with the wrench estimator in dealing with the robot-environment interaction. More details of the results can be found in our paper. Thanks for watching.